types of electromagnetic waves actually. And now we have to again evaluate how much would be the attenuation and what will be the velocity of propagation for this T mode, TM mode and TEM mode actually. So we have to revise that, revise the definitions of the velocity of propagation and attenuation constant for electromagnetic fields actually. So generally what is velocity of propagation is the speed at which the electromagnetic energy travel down a transmission line. All you know, it is proportional to the property of the medium, its permittivity and permeability. So in air, the electromagnetic wave travels at the same speed as the vacuum actually. So it's almost equal to the speed of light. But in other mediums, the speed will slow down based on the dielectric constant, either epsilon and mu value actually. Okay. And the other two factors that defines that wave propagation speed is frequency as well as the angle of incidence, how the wave enters into the waveguide, the angle made by the incident wave with that walls of the waveguide will also decide what is the frequency at, speed at which it travels. Okay. So we commonly use the term velocity factor, velocity of propagation, wave propagation, all tells the same thing actually. So wave propagation or velocity of propagation is generally the speed at which a wave travels in a medium actually. So what is velocity factor is the ratio of the speed of a electromagnetic wave in a particular medium to the velocity of the wave in vacuum actually. So that ratio is called as velocity factor, and the velocity factor for a transmission line is 1 by c root LC. You could have come across this equation where c is the velocity of light and root of L is the inductance and capacitance of that transmission line actually. So velocity factor is a ratio, speed ratio of the wave in a particular medium to that vacuum actually. Okay. Then other two important parameters we often use is the phase velocity and group velocity here. Phase velocity is the velocity of propagation of EQ phase surfaces along a guide. And in a more simple sentence, if you want to say, phase velocity is the velocity of a particular component of a wave actually. That's called phase velocity, the velocity at which a individual component of a electromagnetic wave travel actually. That's called as phase velocity. You can take, for example, a particular frequency, the wave produced by a particular frequency, at what speed it travels, that's phase velocity. Group velocity is the overall envelope. If you have a signal, you'll have an overall envelope of the waveform, right? So what's the speed at which the envelope of the waveform travels down a medium? That's generally called as group velocity actually. So, and the relation between the group and the phase velocity is related to the square of the speed of light, Vp Vg equal to c square. These are all basic fundamental definitions we need in the derivation. Okay. Okay. Then the other one is attenuation factor. So attenuation defines the loss. So how much would be the power loss if you are sending some energy through a transmission line? How much will be the power loss? And that is taken care by the attenuation factor actually. So the attenuation factor is defined as the ratio of power loss per unit length to twice the transmitted power actually. That's a general equation we use in parallel plane waveguides. Attenuation factor is power loss per unit length to square of power transmitted. So if you want to evaluate how much is attenuation in each individual wave configuration like TE or TM, we have to find out how much will be the power lost and then what is the total power being transmitted. Then we take the ratio to find out the attenuation factor. So which you may get as a question, derive the attenuation factor for T waves, TM waves and TM waves. For the three waves, we have to look into this attenuation factor. Then the other parameter of importance is wave impedance actually. You know, impedance is the ratio of the voltage and current actually. It's a complex form of the resistance in a DC condition actually. So similarly, what is wave impedance? You know, impedance, when you say, it's a ratio of the voltage and current, right? So wave impedance is for the field actually. So it's simply wave, it's a definite ratio of the electric field to the magnetic field. So if you want to find out the wave impedance, is it X and Y, then it is Ex by Hy. It means the electric field in the X direction and the magnetic field in the Y direction. So that gives the wave impedance actually. So it's an alternate form of resistance. Resistance we use in transmission lines actually, but when it comes to electromagnetic waves, we have to use this wave impedance. So the impedance in the XY component is electric field strength in the X direction to magnetic field in the Y direction. Okay, that's it. And it's a positive direction. Similarly, in the opposite negative direction, it is minus Ex by Hy. This is wave impedance. So the general definition is the ratio of electric field intensity to the magnetic field intensity is defined as wave impedance. Okay. When you come to attenuation constant of a waveguide, there are two components in a waveguide actually. So one is the medium. The medium is air, that's a dielectric thing actually. Then on the top and bottom, you have conducting plates actually. So you will have losses in the conductor as well as the dielectric medium, that's your air actually. So we have to consider both the losses incurred in the dielectric medium as well as the conducting medium actually. So the attenuation factor includes the attenuation occurred in the dielectric medium as well as the attenuation that takes place in the conducting plates actually. Okay. So now we'll derive the attenuation in a parallel plane guide actually. Okay. So the attenuation factor, first we'll do it for the conductor. Conductor it's easy because we can use a voltage and current relation equations we can use here. Okay. So the attenuation factor is caused by losses in the walls. So if you consider the attenuation caused by the conducting plates on top and bottom of that waveguide configuration, so we can use the voltage and current equation here now. So the voltage, sending in voltage is generally given by V naught e power alpha z e power minus j b z, and the current is I naught e power alpha z e power minus j b z actually. Okay, right. So now we'll first calculate what is the average power being transmitted. If you know the voltage and the current, then we can calculate what is the power actually. So the average power of the signal that is supplied to waveguide is 1 by 2 real part of the product of V into current conjugate. So we have seen V naught e power alpha z is the voltage equation e power j beta z, and the current equation is I naught e power alpha z e power j. And why the minus sign missing here is because in the expression we have the current conjugate actually, so the minus sign is missing here. Then you multiply these two, you get 1 by 2 real part of V naught I naught, and this exponential term reduced to e power minus 2 alpha z actually. Okay. So this is the average power being transmitted. Okay. So now we have to find out the attenuation. What's the rate of decrease of the transmitted power? So the attenuation is variation in the sending power with respect to Z actually. So the partial differentiation of the average power that is being transmitted down the waveguide with respect to Z. So how the power decreases along the direction of propagation, that's the attenuation. And we know this is the sending in voltage 1 by 2 real value V naught I naught e power. So that's the average power we transmitted. So, and when you differentiate this to get the loss actually attenuation. So the rate of decrease is 2 alpha of the average power you are sending in actually. Okay. So this gives the attenuation factor alpha for your waveguide. And this for the conducting plates actually. Okay. Okay. So now we'll see the attenuation factor alpha for the T waves when you look into the air conducting medium. So how the attenuation would be now. The previous case is for the conducting plates actually. Now it is for the field that propagates either in the TE mode or TEM mode or TEM waves actually. Okay. So you look at this earlier slide I've shown there will be 6 equations for the electric magnetic field components, right? So if you apply the condition for TE waves, there is no component of magnetic field in the direction of there's no component of electric field in the direction of propagation, and there exists electric field in the transverse direction only. So such property if you apply, then you'll get only 3 components. So electric field exists only in the y direction, and the magnetic field is in a x direction. That's a property of that. So electric field is perpendicular to the direction of propagation z. So you have ey, and magnetic field is horizontal. So we have magnetic field in the x direction. So we have h x. and we have magnetic field in the direction of Ez because there is no Ez component in TE wave. We have Hz in this, right? So these are the three active components that we have for a TE waves, right? Okay. Okay. So the attenuation factor alpha for it T as it's continued. The amplitude of linear current density in the conducting plane will be equal to the tangential component. So this expression gives the expression for current density, which produces a magnetic field actually. So here the power loss in each conducting plane is proportional to that current density 1 by alpha j zy or z. Okay. So the power loss, the overall power loss for the two conducting planes is generally given by this generic equation 2 into 1 by 2 j square z y r s equal to m squared pi squared c1 square root of omega mu 2 sigma by omega square mu square alpha square. This is a general equation that gives the power loss, right? So power transmitted is again we take the same generic equation 1 by 2 the real value of the E and H component, because in TE wave you have to use the field, not the voltage and current equation. So and the field component that exists is EY, electric field component in the Y direction and magnetic field component in X direction, right? So minus 1 by 2 we'll get C. This is you just substitute the value of EY H X component in this, and then you can simplify and this. And then further, and initially we have assumed that that width spreads to a very large distance actually. But see here we make some approximation. The Z direction for a guide 1 meter wide. The guide is the plates are 1 meter wide and the spacing between them is A actually. So now you can apply these limits, the value of A and the meter length to be 1, and then we can simplify this expression to find out the power transmitted per unit length. Then it becomes beta C1 squared A by 4W. So we simply apply the condition. This is a generic equation, and in this we assume the length of the guide width as well as the conductor spacing. It's taken as A, and then we are working out. And so when you simplify this, you are going to get the power transmitted per unit length is beta C1 squared A by 4 mega. Okay. Now we got the transmitted power, and now we have to find out the attenuation factor for TE waves actually. So the attenuation factor formula is power loss per unit length by 2 times the power transmitted. So the power loss expression is here, and the power transmitted is beta C1 square A by 4, and it is 2 times. So you simplify this, and we arrive at the expression for alpha, right? So once again, I repeat this, how we start the derivation of this. So if you want to find out the attenuation, first thing is, if you are going to solve for T waves, you write down the 3 expressions. So what is the value of the electric field component, the magnetic field component, and what is the component that exists in the direction of propagation. So for TE waves, the electric field exists in the Y direction, perpendicular to Ez, and magnetic field is in the horizontal direction. So you have Hx component. Then there is no component of electric field in the direction of propagation, and you have only Hez. So this is a general equation, and using this, you can find out the power. Use the value of E, Y, and Hx to find out the power transmitted, and then this is a power loss equation. So you can substitute here. So we know the power loss, that's more common for all the 3 things. And you substitute the value of the transmitted power for TE mode actually. Then you can simplify this to arrive at the value of alpha. Okay. So what we observe from this equation is the attenuation factor alpha decreases from infinity at cutoff frequency to a low value at a higher cutoff frequency. So you can just recall the initial slide I told you in the initial slide, waveguides, they cannot be used for low frequency actually. They start conducting power only after a particular cutoff frequency. That is evident from this expression actually. So all waveguides will have a cutoff frequency. They start from a particular frequency from where they permit energy flow actually. So waveguides cannot be used for transmitting signals which are at very low frequency. That's the reason why. So actually waveguides are the transmission lines which have the lowest attenuation even when compared to coaxial cable. But the problem here is we cannot use waveguides for low frequencies. Only after 3 or 4, particularly after 4 GHz, the dimension will be compact and will be practically able to make a waveguide. Below that frequency, it is practically not possible to make waveguides and we cannot use it. So this one unique property, a unique drawback actually of the waveguide. So they can conduct power only after certain cutoff frequency actually. So for T mode, we can arrive at the cutoff frequency using this. So just simplify the following steps. You'll exactly find out what is the cutoff frequency of this. So here, this FC is the cutoff frequency of a particular waveguide. Actually, F is the frequency. At any frequency, you can find out what is the attenuation factor, and also you can solve for this cutoff frequency. And when you look at this expression, the cutoff frequency is decided by two factors. One is the value of A, which is the spacing, the waveguide's spacing between the top and bottom plates, as well as the width. So the dimension of the plates, the conducting walls, and the spacing between them, and then the frequency. These are the three deciding factors for cutoff frequency of a particular wavelength actually. Okay. And similar way we can go for finding the attenuation factor for TM waves actually. So if you look at this for TM waves, you have magnetic field in the y direction. So you have HY component written in the expression, and you have electric field parallel to the direction of propagation. So you have EX, right? So EX component you have, it's in the E is in the X direction, and that magnetic field is in the Y direction, and there is a component of electric field in the Z direction. Okay, so only these three components exist for your TM wave actually. We have HY, EX, and EZ. So after taking these three expressions, so you can proceed in a similar manner to find out what is the power being transmitted as well as the attenuation factor. So once you calculate the attenuation factor and power transmitted by simplifying the three equations, we can arrive at the attenuation factor for TM waves. Okay, so the procedure is similar to what you have proceeded. Only thing we have to start with the right components of H and E actually in the X, Y, and Z component. Okay. And here also for all the TM mode, the cutoff frequency exists actually. So then look at the attenuation factor for TEM mode, and TEM mode you have a similar kind of, but it's more simplified because there is no component of EZ or HZ in the direction of propagation, and you have only EX component and HY component, that's all. So the expression goes very simple, and you can say to find the attenuation for TEM mode actually. Okay, so it is finally 1 by mu A root of omega mu by 2 sigma. One important factor we observe in the expression for that TEM wave is that there is no cutoff frequency here. That F and all doesn't come in this term actually. There is no cutoff frequency. It means the TEM mode supports all frequencies actually. TEM mode supports all the frequencies. So there is no cutoff frequency. When your waveguide supports TEM mode, then there is no cutoff frequency. You can use it for sending all the frequencies actually. But unfortunately, TEM mode doesn't exist in a waveguide actually. If you consider a rectangular waveguide, you can't induce TEM mode actually. You can produce only TM or TE mode, and you cannot produce TEM mode in a metallic waveguide, whether it be rectangle or whether it be cylindrical actually. So this mode propagation will not be possible in rectangular waveguides, and that's the reason why rectangular waveguides or circular waveguides cannot be used for sending low frequency signals actually. So wave impedance already has been designed. So you can design the wave impedance for various ratios actually. Wave impedance in the XY direction. So the first suffix will be the electric field component, and the second suffix will be your magnetic field component. So using this notation, you can define the wave impedance for all the directions actually, for both positive and negative direction as well. It's only a short question you'll get this wave impedance. Okay, so coming to this, what are waveguides? As I said, waveguide is a rectangular metallic tube actually. So In a parallel plate waveguide, so you can have three modes: TE mode, you can have TM mode, you can have TM mode, you can have. But when you close the two sides with again, when it becomes a closed structure, then for this waveguides you have only two modes that exist. That is, you'll be able to launch or send signal only in the two configurations: TE mode or TM mode actually. Okay? And we can make waveguides in two different shapes, whether in rectangular tube or circular tube. Okay. So, and this is just the configuration, the rectangular waveguide, how it looks like. And I told you about cutoff frequency. So what is the minimum frequency that can be launched into a waveguide? That depends upon these two dimensions. A and B is given in this. So the dimension of the waveguide will decide what is the cutoff frequency of the structure actually. So for a particular dimension of A and B, you'll be able to launch both T mode as well as TM mode in a rectangular waveguide actually. Actually, you'll be able to launch both the modes in a rectangular waveguide. But commonly in a practical thing, when you take the radar or a satellite application, all people will use TE mode only. In a rectangular waveguide, they always launch signals in the TE mode configuration. The reason for that is that uh, TE mode will have the lowest cutoff frequency. That is, you will be able to send some more low frequency signals through the dimension is same for a given dimension. When you are launching signal in the TE mode, then it is capable of sending some low frequency signals as well. Say for example, I could say if I'm launching the signal in TM mode, it will it will work from 2 GHz to say 100 GHz. But if I try to launch TE mode, then it could work right from 1 GHz to 100 GHz. So the lower cutoff frequency gets decreased for TE mode when compared to TM mode. And that's called as dominant mode. When you come to waveguide, we always use the definition dominant mode. What do you mean by dominant mode is that the mode that has the lowest cutoff frequency, that's generally called as the dominant mode. Since T mode is dominant in the rectangular waveguide, always we launch signals in that configuration. So circular waveguides are generally not practically used. The reason is the lower cutoff frequency will be higher actually. The cutoff frequency will be much higher. So the bandwidth of the circular waveguide will be very small when compared to rectangular waveguide. So practically people would not prefer using a rectangular waveguide. Okay. So when you come at the advantages, about the structure, if you see, it's a transmission line. You can consider as a transmission line. It's a tube, maybe rectangular or circular in shape, and it is a hollow tube. There's nothing, there's no dielectric material fills inside. It's just a hollow tube which has air as the dielectric in this. Since they are made of metal, no, they are heavy actually. So you can't use it for very long distance. Particularly where they use is in the microwave transmitters, satellite transmitters, radar transmitters. Those are the areas where people use waveguide for transmitting signals. And what's the advantage? Waveguides are easier to because at microwave frequency, there's no other waveguides possible. You have to go only with the waveguides actually, and they are very easy to manufacture because just a tube anyone can manufacture if you give the right dimension. And this is a other important thing actually. They can handle very large power in kilowatts. Actually, it means they can handle. You can give 10 kilowatts, 100 kilowatts of power to a waveguide, but coaxial cables have a power limitation. You can't give kilowatts, megawatts of power to a coaxial cable. They will burn out actually. But waveguides can handle kilowatts and megawatts of powers because it's a metal tube and nothing will happen to it. Actually. No burnout occurs in a rectangle waveguide. And then power loss is very negligible in waveguide. There is no solid material inside a waveguide. There is no dielectric material like that polymer or something you have in a coaxial cable. It's only air. So the loss is very much less when compared to any other transmission line. So if you compare the grade of transmission lines, optical fibers are the best, but you can send in only light into it. And after optical fiber, in terms of attenuation or power loss, these waveguides are the best actually. Waveguides are the best, but you cannot use it for low frequency. That's one major drawback of waveguide actually. And look at the last line. They experience lower loss than a coaxial cable, but suitable only above 1 GHz. That's one major drawback of waveguides. Okay. So difference between circular and rectangular waveguides actually. So when you come to a rectangular or circular waveguide, there are other modes as well. Actually, the people say infinite modes can be launched into a waveguide actually. So in that, particularly people will launch only these two, T10 mode and T11 mode. I'll just briefly what it is. So what is T10 mode is, so you know the T mode, the electric field is perpendicular line. So if you say T10 mode, the field strength will be maximum at the center of that area. If you look at the front end of the waveguide, the electric field strength will be maximum at the center region, and then it gradually dies down along the walls. No, it goes down to zero. So you'll have one half cycle variation. When you look at the left edge of the waveguide, the electric field strength is zero, and then gradually increases, and at the center it is maximum. Then again it comes down actually. So that kind of mode is called as T10 mode. The electric field is perpendicular, and in that the electric field is maximum at the center, and along the edge it goes down to zero. That's called as T10 mode actually. And that we can make by putting the source exactly at the center of the waveguide. If you connect the source exactly, make a hole in the waveguide and put it at the center, then you'll be able to launch T10 mode. And T11 mode is, you'll have two maximas actually. So within the cross section of the waveguide, you'll have two maximas. That's called as TE11. That suffix 11 refers to the number of maximas you get in that. Okay. And for circular waveguide, the dominant mode is T11, but people do not use that, and we practically use only rectangular waveguides. And this is exact component how a waveguide looks like. They make waveguides of short length actually. Then we have to join. If you want to, it's available in just 10 centimeters, 15 centimeters length actually. So if you want to join or take the signal for a longer distance, you have to use nuts and bolts to fix segment by segment, and you can take it to any distance actually. Okay. So this is just a summary of rectangular waveguide. You can launch both the T mode as well as TM mode, but the dominant mode, that is the mode which has the lowest cutoff frequency, is T10 mode. That's what we uh, use for rectangular waveguides. And cutoff frequency will be very less when compared to other modes actually. In T10 mode, the cutoff frequency will be lower. That's called as dominant mode. You can see the text here, dominant mode T10. In that mode, the cutoff frequency is the lowest when compared to other modes actually. And here you have the formula for cutoff frequency. So using this relation, we can make waveguides for any bandwidth you need actually. So you can, for the required cutoff frequency, you have to simply find out the value of A and B. Here M and N refers to that suffix. You have seen, right, 110, T10. That 1 refers to that M, and 0 refers to 0 actually. Okay. So what for T10 mode, M would be 1 and N would be 0, and you can find out the values of AB for this particular mode, and C is the velocity of light actually. Okay. So using this relation, you can design a waveguide for any cutoff frequency actually. The dimensions will vary. Okay. Okay. Thank you.